Today we're going to be talking about decays, and a method of illustrating these decays is through Feynman diagrams. But before we go into that, there are two main kinds of interactions that can cause decays. The first is due to the strong force which we encountered in our fundamental forces lessons. These are called strong interactions. Now, strong interactions only occur between hadrons, and these are your baryons and mesons. So if any leptons are involved, it cannot be a strong interaction. And in strong interactions, strangeness must be conserved. Now, the other type is obviously the weak interaction. And this acts between both hadrons and leptons. So basically, if you see any leptons in a decay equation, it has to be the weak interaction. If the weak interaction is responsible, then strangeness is not conserved. So if you have a +1 or a -1 strangeness at the beginning, it will typically go to 0 strangeness at the end. So this could be an example of a decay that you might encounter in your questions. And from the off, you can immediately see that there is some unfamiliar particle present, this lambda here, this lambda particle. But you'll be told what the quark configuration of this particle is, and you're told here that it has a quark configuration of up, down, and strange. And you're told that this interaction is due to the strong interaction, therefore only has to be between hadrons, and strangeness must be conserved. So let's look at all the other factors that have to be conserved in any decay. Well, the baryon number must be conserved, the charge must be conserved, the lepton number must be conserved, and in this case, the strangeness must be conserved. So what's the baryon number of this first lambda particle? Well, we know that the baryon number of each individual one of these quarks is plus a third, so it has a baryon number of 1. We know that the baryon number of a meson is 0, and for a proton, it's also 1. And I forgot to mention, we are trying to find out what this particle, this unknown particle here is. We don't know what it is. We want to figure out what that is. So due to this, we can clearly see that this must have a baryon number of 0, because we know that baryon number must be conserved. Now let's look at the charges. The charge of this lambda particle is, well, up is a charge of plus 2/3, and down the strange each have a charge of minus a third. So this here actually has 0 charge. The pi plus, well, we're told it has a positive charge on it. We know that's a charge of +1. And this proton, we know, has a charge of +1. So this means that the charge of this unknown particle has to also be 0. Because again, we need the charge to be conserved before and after. We're told that the strong force is at play here. So we know no leptons are involved, but if you were to go through each individual particle, you will find out that the lepton number of this particle, and the proton is all 0. So therefore the unknown particle must also have a lepton number of 0. And here's where the strangeness bit comes into play. We're told it's a strong force. And now the strong force means that strangeness must be conserved. So let's quickly look at the quark configuration of the pi plus meson and the proton. Well, the pi plus meson has a quark configuration of up and anti-down. And the proton has a quark configuration of up, up, and down. So if we look at the strangeness of each of these particles, this lambda particle has a strangeness of -1. This pi plus meson has a strangeness of 0. This proton has a strangeness of 0. So this unknown particle that we're trying to find out must have a strangeness of -1. So we need a particle that typically is going to be a hadron that has 0 baryon number, 0 charge, 0 lepton number, and a strangeness of -1. Because it has a strangeness of -1, we can pretty much guarantee that it's going to have a strange quark in it. And therefore, if we look through the other factors, in order to get a baryon number of 0, we know that this other quark here must be an antiquark. And in order to get the charge to 0, this has to have an opposite charge to the strange quark. The strange quark has a charge of minus a third. So we need an antiparticle that has a charge of plus a third. And there are two. There's the anti-down and the anti-strange. And because we need an overall strangeness of -1, this other quark has to be the anti-down. So if you were to look at your table of mesons, this here would be a K0 meson. Now, a quick little hack that can sometimes save you time in exams, but it isn't really the proper way to go about this is to just simply look at the quark configurations. You can see on the left hand side that you have two up quarks. So therefore on the right hand side you must also have two up quarks. And you see that there's one strange quark. And because it's a strong nuclear force or the strong interaction, there must also be a strange quark on this side. Now you may notice that you have a down and an anti-down. And remember from our annihilation video, a down and an anti-down quark can annihilate to cancel out each other. So these two could disappear. But we can see here that the down is also present in the proton. So therefore, you also need an anti-down present in this other particle. So you could quite quickly gather that the quark configuration of this other particle is of strange and anti-down. And you could use this quark configuration as just a check to make sure that you've done the right thing. So now we're going to go and have a look at Feynman diagrams. These are a very good way to represent interactions and decays. So let's start with something simple as two protons interacting and repelling each other. What you do is you draw these two protons coming in, and these protons are going to experience the electromagnetic force and repel each other. So you know that there's going to be some interaction between them, and this interaction is due to this virtual photon that we discussed in our fundamental forces video. And what it's going to do is it's going to send a message from one proton to the other to repel each other. So what you're going to see is these two protons coming in and then getting repelled away. That's quite a boring Feynman diagram, but it's pretty good at introducing you to the concept. You have these two particles coming in and these two coming out. Now the most interesting Feynman diagrams actually come through weak interactions. So let's look at a few examples. The first one is this beta minus decay. So the first thing before you do any Feynman diagram is you kind of need to know what the decay equation is. In this case, you have a neutron, which is going to decay into a proton and an electron. And remember from our leptons video, we know that lepton number has to be conserved in this case. We know that the lepton number of the neutron is 0, the proton is 0, and the electron is plus 1. So therefore we need an anti-electron neutrino in order to conserve the lepton number. So this is our decay equation. This time we're going to have one neutron coming in. And we know that a proton is going to come out of it. So we're going to draw this proton this way. And we know that due to this interaction, which is denoted by this squiggly line, we're also going to get an electron coming out and an anti-electron neutrino coming out. And because this is the weak interaction, we need one of these exchange particles of the weak interaction to carry out this decay. So let's remind ourselves of what they could be. So we have the W plus boson and the W minus boson. And you need to decide, well, which one is going to be responsible for this particular decay. Well, let's have a look. We know that this neutron has a charge of 0, and this proton has a charge of plus 1. So as it comes to this point here, you have an overall charge of 0 because of this neutron, but then a plus 1 charge goes that way. So in order to balance it out, you need a charge of minus 1 going this way. So in this case, you're going to have your W minus boson responsible for this decay. And you might ask, well, why is the neutron and the proton on the same side? And that's because the neutron is technically being converted into the proton, and in doing so, it just emits an electron and an anti-electron neutrino. So this basically is why this proton's on this side, because then it's basically showing that the neutron is getting converted into the proton. That kind of makes common sense because they're both baryons. So we have a beta minus decay. There's also something called a beta plus decay, which is basically the opposite. It's basically when a proton gets converted into a neutron. And in doing so, in order to conserve charge, lepton number, etc., we need a beta plus particle, which is going to be your positron. And in this time, you're going to just have a regular electron neutrino. And again, if you want to draw a Feynman diagram, we have a proton coming in, and it's being changed into a neutron. Into this point here, we're having a proton coming in, which is a charge of plus 1. The neutron has 0 charge, so therefore we need a positive charge coming this way. So the responsible exchange particle is your W plus boson, because this once again is due to the weak interaction. And you know this because it's involving leptons. So then you just draw your positron coming out and your electron neutrino coming out as well. Now there's something called electron capture, which is where a proton interacts with an electron and they fuse together basically. I want you to try and finish off what's going to happen in this decay, what you think might be the answer. And you can do this by conserving baryon number, charge, and lepton number. And remember, you don't need to conserve strangeness here because there is no strangeness to start off with. So pause the video and try this out. If you try it out, you're going to end up finding out that you get a neutron and an electron neutrino. So how about, with this finished decay equation, try drawing the Feynman diagram. And I'll let you know that you don't need to include a exchange particle for this case. So if you want to draw the Feynman diagram, you have a proton coming in and with an electron as well. They interact, and the proton gets converted into a neutron, and an electron neutrino gets released as well. So you'll get something that looks like this. Now, the point of some exchange particles in these decays is to mainly transfer energy, momentum, force, and in some cases, charge. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.